So actually we learned about the exponential coordinate representation. Using small SO3 can be large SO3. So this small SO3 was some kind of skew symmetric matrix. And this one become rotation matrix. So this one was done by exponential. So the skew symmetric means this kind of matrix. Yeah, this kind of matrix can be converted to rotation matrix. So actually, when we know if we know the rotation axis, we can find the rotation matrix. And also, this angular velocity vector can be represented by unit vector. Some unit vector here. And then if there is some rotation angle, actually this one is multiplying time t. This one becomes theta. Then we can find this kind of rotation matrix. So we learned about this one. So this component become here, and using exponential, we can describe the rotation matrix R like this shape. And also, if we take the log of this one, it becomes like this. So this logarithm describes this one. So that was the exponential coordinate representation. So we deal with about only the rotation. We only deal with the rotation, about the rotation. But the rigid body motion, including rotation and also translation. So in this time, we can expand the concept of SO3 to SE3. So actually this one is a special Euclidean group. So Euclidean means Euclidean include the rotation motion and translation motion. So this rotation becomes a homogeneous transformation matrix. And also this skew symmetric becomes the twist. Actually, the normalized we use in here, normalized twist, there is a screw. We use a screw here and the theta. The shape, so the shape is very similar. But actually, this one has sometimes some kind of skew symmetric matrix, but this one has the shape of like this. As we already learned, this one is 4x4 matrix. So this SE3, small SE3, when we take the exponential of this one, then we can get homogeneous transformation matrix T that is large SE3. And the reverse case also, in the case of reverse case, we can use the log in here, then we can get this SE, small SE3 form. So this kind of mechanism also work in SE3 dimension. We only learned about the SO3 case, but we can expand to SE3. So let me think about this one. Let us think about this one. Actually, by taking the exponential in here about this one, we can write down this equation. So let's think about this. The S means the screw axis. So S means screw axis, and this one is SE3 form of screw axis. So let's think about this. The bracket S is this one. It is, as I already told, this one is small SE3 form. And if we take the square of this one, it becomes like this. And also, if we multiply one more time, we can get this one. Because this exponential term can be described by the Taylor series. We already learned. Then we can put this term here and put this term here and put this term here. Then we can summarize this equation like this. So the first element becomes this, and second element become this, and 0, 1. If you see this term equal to this one, and this one, the V term is always same in here, V. So we can simplifying like this, and also we can define this term as a new term, G theta. So in here, exponential bracket omega theta means this one is same one with this one. So in here, because this equation equal to R, and also this one is because this one is homogeneous transformation T, it should be rotation matrix. So this one is the same as rotation matrix, and this one is equal to P. So actually this P term is G theta multiplying V. So the G theta was this term, and this term can be simplified like this. So this procedure can be checked the page 71, and this procedure can be checked in page 90 in your textbook. So I will not explain in detail in here. So let me summarize in here. The screw axis is omega and V. So in case of omega, norm of omega equal 1, this exponential coordinate representation is simplified like this. And in the case of omega equals 0 and the size of V equal 1, it means pure translation. There is identity matrix in here, and V theta, there is position vector. So we can check these two cases. even though the norm of angular velocity vector is 1, we can have some this kind of 0 root 2 over 1 root 2 over 1. This one has norm has 0 square plus square plus, then this one size has 1, but it has some kind of component like this. So we can calculate the rotation vector using this equation, and also we can calculate the position vector using this one. So when we calculate this one, we use theta and the omega, and also we use v. So we can use this equation, and also there is pure rotation case. In this case, we can simply calculate the homogeneous transformation T matrix using this equation. So this relationship, logarithm and exponential relationship, also valid in this case. So when we describe the rigid body motion using screw axis with exponential coordinate, then we can represent the homogeneous transformation T, the element of large SE3 can be converted to small SE3 like this. Actually, the small SE3 twist, there is twist was this some kind of this we describe like this. But if we use the screw, in the case of screw, the size of screw is 1. So we multiplying the magnitude theta. So in the case, we can represent like this. So this is also small SE3 form. So this one. So let's think about the example 3.26.